Hello. In this video, we're going to look at a particular type of power series called a Taylor series or a Taylor polynomial, and a subset of that called a Maclaurin series. So these are series in the form that's given here, where we see it's an infinite sum, an infinite polynomial, as every power series is, and it's centered at A, where we've got powers of x minus A. The coefficients for these series are calculated by evaluating the various derivatives. So when k equals 0, we would consider the zeroth derivative of f to be the actual function, and then we have first derivative, second derivative, third derivative, so on. Evaluating each of these derivatives at a and dividing it by k factorial, where k is correlated with the power of x. And a Maclaurin series is simply a Taylor series, which is centered at 0. So both of these series can be used to make a polynomial approximation to transcendental functions, and very commonly we do this for trig and exponential and logarithmic functions. So let's suppose we start with the function f at x equals sine x. Now if I want to center it at 0, then what I'm going to get is a polynomial approximation to the sine function that is closest around 0. So if I'm wanting to estimate the value of sine 0.6, for example, 0 is a good center. If I'm wanting to estimate the value of sine 3.7, then I probably want to choose a different center. But there's two ways to make my approximation better. Choose a center closer to the value I'm trying to assess. And there's a trade-off here because I want my center to still be close to the value I'm looking for, but also to be a value for which I can easily calculate the value of that sign and the various derivatives of it. And the number of terms of this polynomial I want to use. The more terms I use in this infinite polynomial, the closer my approximation will be. So let's find the first four non-zero terms of the Maclaurin series for f of x. So the first term, in other words, if k equals 0, if k equals 0, then what we've got is the actual value of the function at 0, because 0 is the center of the Maclaurin series, over 0 factorial, which recall is 1, times x to the power of 0, which is also 1. The sign of 0 is just 0, so this is 0 over 1 times 1. So the first term, the constant term of this Maclaurin series is just 0, so that actually doesn't count towards my first four non-zero terms. Once I start finding derivatives, so the first derivative of x is cosine of x, and that evaluated at 0, the cosine of 0 is 1. So now I actually am going to have a non-zero polynomial. This one is going to be 1, which is the value of the first derivative, over 1 factorial, which is just 1, times x to the power of 1, so just x is this term. Once I go on to the second derivative, well, the second derivative of sine is the derivative of cosine, which is negative sine of x. And when I evaluate this one, I get 0 again. So this is going to be a 0 term, so I don't need to bother figuring out what it is. So this is when k equals 1, when k equals 2. When k equals 3, I'm dealing with the third derivative, so I'm just going to write it this way as opposed to using 3 apostrophes. This is going to be negative cosine of x. So the third derivative evaluated at 0 is going to be negative 1. So this is going to give me a term of negative 1 over 3 factorial times x cubed, which is negative 1/6 x cubed. And then when I find the fourth derivative, this is going to be negative sine. So sine x, well, this actually returns me back to my original function. So what I see is I'm actually going to end up in a cycle. So that's going to be helpful. That means I don't have to keep finding derivatives by hand. It does mean here I have a 0 term. So what this means is I'm going to have 0 terms for each time k is even. And so I'm only going to have non-zero terms when k is odd. So I need to figure out then, what do I have when k equals 5 and when k equals 7. Now, because I'm going in circles, when k equals 5, the derivative is going to be negative sine x, which means, the derivative is going to be cosine of x, which means that I'm going to have 1 in my numerator. And when k equals 7, that is when I'm going to have a negative 1 in my numerator. So 1 divided by 5 factorial, which is 1 over 120, times x to the power 5, and negative 1 divided by 7 factorial, which is 5040, times x to the power 7. So the first 4 non-zero terms in this expansion, sine of x is approximately equal to x minus 1/6 x to the power of 3 plus 1 over 1/20 x to the power of 5 minus 1 over 5040 x to the power of 7. Now, thinking about what that is, that's a degree 7 polynomial. It's going to have some pretty, let's say, wiggly bits, a number of direction changes. And since we know that the sine function is, well, it's a wave function, this is essentially going to give me those waves pretty closely in the middle of the function. In other words, symmetric around 0. I can also notice that as I get further out, I can predict that the coefficients of those terms are going to get quite small. I'm going to have ever increasing denominators with numerators that are just going to be 1 or negative 1. And since I'm using this ideally to make approximations for values of x that are close to 0, the more terms I add on, it's not changing the overall value very much. So typically we can get a pretty good approximation with just this many terms. And if I actually look at the graphs, so in red here, we have the graph of y equals sine x. And in blue, I've written those 4 terms, so the degree 7 Maclaurin series here. And we can see that we get an actually pretty good approximation until, I don't know, roughly here-ish. So kind of pretty close to negative pi to pi is a pretty good approximation here. The closer I get to negative pi or pi, the further off my approximation is going to be. So if I wanted to estimate a value, like for example, what is the sine of 3, I probably would either add another term onto this or choose a different center. If I chose a different center, I wouldn't need as many terms, but you can see that if I was predicting values in this region, this polynomial would give me a very close estimate.